Hello and welcome back to the third session on symmetry. So in the first session we discussed about the basic idea of symmetry and the applications of symmetry, and in the previous session we discussed in detail the concept of line symmetry and the lines of symmetry for regular polygons. Now in this session we are going to discuss about rotational symmetry. We first define what is rotational symmetry. That is what we'll be doing the first thing. Then we discuss a little bit in more detail about what do we mean by rotation and how do we represent rotation mathematically, and then we go on to find out a method to find out the rotational symmetry for regular polygons. So let's move on and discuss what do we mean by rotational symmetry. The rotational symmetry is defined as if after a rotation, note the word rotation here, if after a rotation an object looks exactly the same, we say that it has rotational symmetry. So there are two important concepts here. There has to be a rotation involved, and after the rotation the objects has to look exactly the same. Now let us try to understand this using an example from the textbook. Now this example is it's a pictorial representation of a paper windmill. So the paper windmill has four corners, you can say, or four flaps, you can say, and each flap, right, we have labeled it as A, B, C and D here, and this is the starting position. Let's say that the figure number 1 is the starting position for our paper windmill. Now what I'm going to do is I rotate this paper windmill by 90 degrees in an anti-clockwise direction as is shown by this arrow. So what it does is that the position of A moves 90 degree in the anti-clockwise direction, and similarly happens to B, C and D. So you can see the new image here where A is, the position of A is here. So we are just tracking the point A. We have just taken one point A for simplicity and we are just tracking it as to what is the location of this point when we are rotating. So let's say this is the figure number 2. Now one thing you should observe is that when we have rotated this image by 90 degree, the image here and here, it looks the same. There is no change in the way the image is looking. We move on ahead further and we rotate this image again into anti-clockwise direction by 90 degrees and we get the third image. Again you see that this is still looking the same. There is no change as to how it is, but of course the point A that we are tracking is now here. Now we again give one more rotation by 90 degrees and then we see that the point A has now traveled here and still the image is looking the same. Give one more rotation. Let's say this is figure number 4, and then we are giving one more rotation, anti-clockwise rotation by 90 degrees, and then we come back to the starting point from where we started. If you see the starting point in figure 1, A is here and this is the A, right? So this is figure number 5. Now just imagine that we do not have any of these 4 letters for the flaps, that is A, B, C and D. If these were not there, and if I would have done this rotation by 90 degrees, it could have been clockwise or anti-clockwise. We wouldn't have been able to know that this is a rotated image of this paper windmill. Now this is a particular scenario, this is a particular image which is exhibiting rotational symmetry. So now let's try to understand this in light of the above definition. So what our definition says is, if after a rotation, so we are rotating this in anti-clockwise directions by 90 degrees, all these images, an object looks exactly the same, right? So if we see this object, this paper windmill, in all these 4 rotations that we have done here, it is looking exactly the same, right? And therefore it is said to exhibit rotational symmetry. So this is what we mean by rotational symmetry, and then we have understood it using an example. Now having said that, let us understand rotation into more detail, because rotational symmetry is related to the rotation of an object or a shape, and rotation is involved. So it's worthwhile for us to know what is rotation. So rotation is the movement of an object around a fixed point. Now the most common example that you would take is that of a clock. in a clock you have minutes, you have an hour hand, you have a yeah, this is the hour hand, this is the hour hand, this is the minutes hand, and this will be the seconds hand. Okay, so yeah, just taking the conventional normal convention. Now what is happening, all these three hands of the clock, they are rotating along this fixed point. You see, they rotate in this direction, the seconds hand will move in this direction, and so on. So this, they rotate along this fixed point, and that is what we, okay, just let me write the numbers here, 12, 3, 6, 9, around the fixed point. So these three hands of a clock are set to rotate along around this center, and this center, right, around which these hands are rotating, is said to be the center of rotation. So this point is the center of rotation for the clock, and the angle of turning during rotation is called the angle of rotation. It's just the small angles that the seconds or the minutes or the the minutes or the hour hand makes, that is called as the angle of rotation. We'll see about this angle of rotation in a bit more in detail. Now it is important to know what do we mean by a full turn. For example, when a seconds hand, right, it starts from position 12 and come back to position 12, going through a complete round here, complete turn, it is said to have covered 360 degrees of rotation. Similarly, half a turn, that is starts from 12 and comes till 6 here, it is said to have completed 180 degrees. And a quarter turn implies 90 degrees, that is starts from 12 and it ends at 3. So that is quarter turn. Now this is about rotation. What do we mean by rotation? And as we discussed right now, one of the most common examples of rotation is the minute, hour, and the seconds hand for the clock. Okay, so that was about rotation. Now let us try to find out the rotational symmetry for regular polygons, as we did for finding out the line symmetries for the regular polygon. And again, in this case we will take the example of a square, as we did for line symmetry as well. So this is the example that we take from the textbook. Now if you remember the initial example for the paper windmill that we followed, so we will be following a similar approach here. So what we need to do is we first need to find out a fixed point along which we are going to do a rotation. So this center of the square here is our point of rotation. Okay, and we also take up a point P just for tracking purposes, for our convenience. So we have put this point P here, and then we decide that okay, we are going to rotate the square by 90 degrees. Okay, now why we have taken 90 degrees is something which I am going to address a little later. So now let's see what happens. Now this is our starting point 1, and then we rotate this figure by 90 degrees so that this P point now comes downwards. If you see the size, if you see the way the square looks, there is no change, it looks the same, right? So it does have rotational symmetry. Then we again rotate it further by 90 degrees as is shown here, and now this P point comes over here. Okay, so again we see that the square is still looking the same, there is no change in the way the square looks. Then we give one more 90 degree rotation as is shown here, okay, for this one, and then we get the P. And then when we give one more rotation here in the fourth part, when the P is traveled here, we get the starting location of the P as was in the figure 1. Now observe a few things about this experiment. First one is the center of rotation is the center of square. Okay, this center of square. So we are rotating the square along its center. The angle of rotation is 90 degrees. Now you might be thinking, why 90 degrees? Why not any other angle? Well, the reason is we are intended, or we would like to find out an angle in which the square looks the same. So that comes out to be a 90 degree angle. And then You should also observe that the direction of rotation is clockwise. We are going in the direction of the hands of a clock like this. Okay, and we say that the order of rotational symmetry is 4. This we say because the point P comes back to its starting point after 4 rotations. If you see, right, I rotate this object 4 times, then only P comes back to its rotation. So it simply implies that how many times can I rotate the object before it comes to its original position and still it looks the same. Okay, so this is a quick introduction about rotational symmetry and how do we find out rotational symmetry for a regular polygon that is square. Okay, I'll be talking a little bit in